The elements in group 17 are fluorine, chlorine, bromine, iodine and astatine. These elements are collectively referred to as the halogens. The term halogens is derived from the Greek words halo, which means salt, and gens, which means bond. That is, the word halogens means salt-producing in Greek. In other words, these elements react with metals to form salts. Now let's look at the electronic configuration of the group 17 elements. The valence shell electronic configuration of these elements is Ns2np5. So, it is evident that these elements have 7 electrons in their valence shells. The electronic configurations of these elements are listed in the table here. You can see from the table that the valence shell is short of an octet by 1 electron. As these elements need 1 electron to attain stable octet or nearest inert gas configuration, they have a strong tendency to either gain 1 electron to form an ionic bond or share an electron with another atom to form a covalent bond. The halogens constitute the most reactive group of nonmetals. The high reactivity of the halogens is attributed to their strong tendency to acquire or share an electron to attain the nearest inert gas configuration. Let's now discuss the occurrence of these elements. Owing to their high reactivity, the halogens do not occur in free state, but in combined state in nature, except for astatine. Note that astatine is radioactive and has a short half-life. The table here lists the abundance of these elements in the Earth's crust by weight. You can see from the table that fluorine and chlorine are relatively more abundant than others. Note that fluorine is the 13th and chlorine the 20th most abundant element by weight in the Earth's crust. Fluorine occurs widely as insoluble fluorides, such as fluorspar, cryolite, and fluorapatite. Of these, the main source is fluorspar. Small amounts of fluorine are present in soil, plants of river water, and the bones and teeth of animals. Chlorine, bromine, and iodine are present in seawater in the form of chlorides, bromides, and iodides of highly active metals like sodium, potassium, magnesium, and calcium. Of these, the most abundant is sodium chloride. Seawater consists about 1.5% by weight of sodium chloride. The dry beds of seas also contain large deposits of sodium chloride along with smaller proportions of calcium chloride and carnallite. Iodides are found in traces in seawater. The principal source of iodine is seaweeds and crude chili salt petre. The percentage abundance of iodides in these compounds is given here. The atomic properties of group 17 elements are given in the table here. Let us begin our discussion with the trends in atomic and ionic radii. A comparison of these two tables shows that as we move down the group, the atomic radii and ionic radii increase due to the addition of a new principal energy level in each successive element. However, these elements have the least atomic radii when compared to other elements in the corresponding periods. This is because of maximum effective nuclear charge. Now let's look at ionization enthalpy. Group 17 elements show very high values of ionization enthalpy. As a consequence, the atoms of these elements have little tendency to lose electrons and form positive ions. However, as we move down the group, the value of ionization energy decreases. This is due to the gradual increase in the atomic size, which reduces the force of attraction between the valence electrons and the nucleus. You can see from the table that the ionization enthalpy of fluorine is appreciably higher than any other halogen, which is attributed to its small size. Halogens have the maximum negative electron gain enthalpy in the respective periods. This stems from the fact that in the atoms of these elements, the valence shell is short of an octet by only one electron. Moreover, these elements have the maximum effective nuclear charge and the smallest atomic radii in their respective periods. Hence, these elements have a strong tendency to accept an electron and attain nearest noble gas configuration. The electron gain enthalpy becomes less negative on descending the group. However, fluorine has less negative electron gain enthalpy than chlorine. That is, chlorine has the maximum negative electron gain enthalpy among all the elements. It is because of the small size and compact 2p subshell of the fluorine atom. Owing to the small size of the fluorine atom, the incoming electron experiences a greater amount of repulsion from the electrons that are already present. In other words, the electron-electron repulsions between the incoming electron and the electrons already present outweigh the attraction between the added electron and the nucleus. The halogens have very high electronegativity values. You can see from the values of electronegativity in the table that the electronegativity decreases gradually on moving down the group from fluorine to iodine due to the corresponding increase in the atomic radii. Note that fluorine is the most electronegative element in the periodic table. Group 17 elements are also known as halogens. You know that these elements are the most electronegative elements among all the elements in the periodic table. Let us first study the physical properties of group 17 elements. Physical properties include physical state, color, solubility, metallic character, density, melting and boiling point, and bond dissociation energy. Let us look at each in turn. Group 17 elements appear in different physical states. For example, fluorine and chlorine are gases. Bromine is a liquid, while iodine is a solid. All these elements are diatomic in nature. Group 17 elements exhibit different colors. This is due to the fact that they absorb radiations from visible light, and the valence electrons are easily excited to higher energy levels. By absorbing different amounts of radiations, they appear in different colors, like fluorine is pale yellow, chlorine is greenish yellow, bromine reddish brown, and iodine dark violet. Of these elements, fluorine and chlorine are soluble in water. Bromine and iodine are sparingly soluble in water, but completely soluble in organic solvents like chloroform, carbon tetrachloride, carbon disulfide, etc. You know that as you move down in a group, metallic character increases. The same trend is observed for group 17 elements. Due to high ionization enthalpy values, all these elements are non-metallic in nature. The non-metallic nature decreases as we move down the group. Therefore, the last element, iodine, is a solid with a metallic luster. The densities of these elements increase regularly from fluorine to iodine, as shown in the table here. The melting and boiling points of these elements increase regularly from fluorine to iodine due to the gradual increase in their atomic size, as shown in this table. The bond dissociation energy of these elements gradually decreases from top to bottom, except for fluorine. Now let us discuss the oxidation states of group 17 elements. You know that the general electronic configuration of group 17 elements is Ns2Np5. So they have 7 electrons in their valence shell. Hence, they need only 1 electron to complete their octet and attain noble gas configuration. The octet can be achieved either by gaining 1 electron or by sharing 1 electron. As a result, the common negative oxidation state of these elements is -1. These elements exhibit +1, +3, +5 and +7 oxidation states along with -1 oxidation state as shown here. Fluorine exhibits only -1 oxidation state because it does not have d orbitals in its valence shell. It is the most electronegative element, so it cannot show any positive oxidation state. Chlorine, bromine, and iodine all exhibit 4 different oxidation states, +1, +3, +5, and +7. This is because of vacant d orbitals in their valence shells. The positive oxidation states of these elements are observed in some compounds like interhalogen compounds, oxides, and oxo acids. These elements exhibits +1, +3, +5, and +7 oxidation states in interhalogen compounds of AX, AX3, AX5, and AX7 types, as shown in this table here. These elements exhibit oxidation states from +1 to +7 in their oxides, as shown in this table. Group 17 elements exhibit +1, +3, +5, and +7 oxidation states in their oxo acids like hypohalous, halous, halic, and perhalic acid series. Group 17 elements are more reactive than all other elements in the periodic table. They react with metals and non-metals to form halides. The reactivity of these elements decreases down the group. All these elements are ready to accept an electron from other elements. Hence, they are all good oxidizing agents. The oxidizing capacity of these elements decreases down the group. So, fluorine is the strongest oxidizing agent among them. Fluorine oxidizes other halide ions. In general, a halogen oxidizes higher halides to their respective halogens, as shown here. You know that the oxidizing capacity of these elements decreases down the group. This is confirmed by their reaction with water. Fluorine oxidizes water to oxygen gas, whereas chlorine and bromine produce their corresponding products, like hydrohalic and hypohalous acids. The reaction of iodine with water is non-spontaneous. In an acidic medium, iodide ions are oxidized by oxygen, as shown here. When these elements react with hydrogen, they give hydrogen halides. These hydrogen halides react with water to give hydrohalic acids. The acidic strength and bond lengths of these halides increases, and bond dissociation energy decrease from top to bottom. The melting and boiling points of these halides gradually increase from top to bottom, except for hydrogen fluoride. This is due to the high electronegativity and small atomic size of fluorine. Halogens form many oxides with oxygen. The stability of these oxides increases down the group. Fluorine forms only two oxides, OF2 and O2F2. These two are thermally stable at room temperature, and both are fluorinating agents due to the high electronegativity of fluorine. For example, O2F2 fluorinates plutonium to plutonium hexafluoride. Chlorine forms the oxides Cl2O, ClO2, Cl2O6 and Cl2O7. All these are powerful bleaching agents. ClO2 is used as a bleaching agent in the wood pulp, water purification and paper industries. Bromine forms the oxides Br2O, BrO2. All these are less stable, exist at very low temperatures, and act as powerful oxidizing agents. Iodine forms I2O4, I2O5, and I2O7. All these are solids and are insoluble in water. Among these, I2O5 is a good oxidizing agent. Halogens react with metals to give metal halides. For example, chlorine reacts with calcium to give calcium chloride. All these metal halides are ionic in nature. The ionic nature of monovalent metal halides decreases from fluorine to iodine. However, if the metal exhibits an oxidation state of more than 1, then the halide at the higher oxidation state is more covalent than the lower oxidation state. For example, SnCl4, PbCl4, SnCl5 and UF6 are more covalent than SnCl2, PbCl2, SnCl3 and UF4. Due to electronegative difference and atomic size variations, these halogens combine amongst themselves to form complexes known as interhalogen compounds of the type AX, AX3, AX5 and AX7 as shown here. Here, A is a large halogen and X is a small halogen. Let us now study the anomalous behavior of fluorine. Like all p-block elements, halogens also start from the second period in the periodic table. Fluorine shows a difference in some properties with respect to the other elements in the group. This anomalous behavior is in properties like ionization energy, electronegativity, bond dissociation energy, electrode potentials, electron gaining enthalpy, ionic and covalent radii, melting point, and boiling point, as shown in the table here. This is due to the high electronegativity, small atomic size, low bond dissociation energy, and no availability of d orbital in the valence shell.